here's a 3, and here's 3 squared. And 3 squared is equal to 9. And here's the square root of 9, and that's equal to 3. Remember that 9 actually has 2 square roots, both positive 3 and negative 3, but that symbol means only find what's known as the principal square root, which also means the positive square root. So when we write the radical symbol, square root of 9, we're just looking for the positive square root, the 3. Since 3 squared is equal to 9, and the square root of 9 is equal to 3, then by substitution, the square root of 3 squared is equal to 3. Well, now let's use a variable. What if n is equal to 3? Then n squared is equal to 9. And the square root of n squared is equal to 3. And by substitution, the square root of n squared is equal to n because n was equal to 3. But now we'll start with negative 3. Negative 3 squared is also 9. The square root of 9 is 3. The square root of negative 3 squared is also 3 by substitution. So what if n is negative 3? N squared is equal to 9. The square root of n squared is equal to 3. And the square root of n squared is also equal to the absolute value of n, because remember, n was equal to negative 3. And since we know from line 3, the square root of n squared is 3, but n is negative 3, we need to put the absolute value symbols around our n so that when we take the square root of n squared, which of course is 9, we get positive 3 instead of negative 3. We'll look at the 3 again, and now we're going to cube it. And of course that's 27. And then we're going to take the square root of 27, which in simple radical form is 3 root 3. So the square root of 3 cubed is 3 root 3. Now if n is equal to 3, then n cubed is 27. And the square root of n cubed is 3 root 3. And another way to write that is n root n, because n is equal to 3. Here's negative 3. Negative 3 to the third power, or cubed, is negative 27. And if we try to take the square root of negative 27, and that's not a rational number, because negative numbers do not have real number square roots. Therefore, the square root of negative 3 cubed is also not a rational number, because negative 3 cubed is equal to negative 27. Well, let's let n equal negative 3. N cubed is negative 27. And once again, the square root of n cubed is not a rational number. We don't need absolute value symbols when we're taking square roots of variables cubed, because we're assuming that if we can simplify the square root of a number, that the number inside the radical is a real number in the first place. So that means that if we have a variable cubed and we're taking its square root, the variable must be positive. And that brings us to this rule: the square root of a perfect square is equal to the absolute value of its base. And now we'll look at some examples. So the square root of n squared is equal to the absolute value of n. The square root of n to the fourth is equal to n squared. We don't need the absolute value symbols because n squared is always a positive number in the first place. The square root of n to the sixth is equal to the absolute value of the n cubed. We need the absolute value symbols here because sometimes n cubed is a negative number. So when we're simplifying, we need to put the absolute value symbols around it. And now we'll move it over and do some more. The square root of n to the eighth is equal to the n to the fourth. We don't need absolute value because whether n is positive or negative, n to the fourth is always positive. But the square root of n to the 10th is equal to the absolute value of n to the 5th, because once again, n to the fifth could be a negative number if n was negative in the first place. And then finally, the square root of n to the 12th is equal to n to the 6th. A real number to the 6th power is always positive, so we do not need the absolute value symbols. And you're probably seeing some relationships between odd exponents and even exponents. I hope you are. Well, now let's look at some square roots of some odd exponents. We already know that the square root of n cubed is n root n. And once again, we don't need any absolute value symbols because we're assuming that if we can find a real number value for the square root of n cubed, then n cubed is positive in the first place. So the square root of n to the fifth is n squared times root n. The square root of n to the 7th is n to the 3rd times root n. The square root of n to the 9th is n to the 4th times root n. And the square root of n to the 11th is n to the 5th times root n. And we're going to do one more. The square root of n to the 13th is n to the 6th times root n. So when you're taking the square root of a variable with an odd exponent, you never have to worry about absolute value symbols because you're making the assumption that you're simplifying an expression that is a real number in the first place. Well, let's take a look at this problem. Root 48 times x to the 6th, y to the 2nd. Well, of course, we've already done root 48 by itself. We'll redo it here. 48 is the same as 16 times 3, and the square root of 16 is 4. And now we have x to the 6th, which is the same as x to the 3rd times itself, and y to the 2nd, which is the same as y times y. So we can take the square roots of both of those, but since the exponents were even, we need to put those in absolute value symbols. So our final answer is 4 times the absolute value of x cubed y times root 3. Here's 5 times the square root of the quantity 72 x to the 16th y to the 5th. Well, we know that 72 is 36 times 2, and the square root of 36 is 6. We bring it out, we multiply it by the 5 that's already there, and we get 30. And now we look at our two variables. X to the 16th, of course, when we take the square root, we get x to the 8th. And y to the 5th, that's an odd number, but that's y to the 4th times y. So we leave a y inside. Bring out the y to the 4th after we take the square root, which gives us y to the 2nd. And, of course, the square root of x to the 16th is x to the 8th. And x to the 8th and y to the 2nd are always positive numbers. So an absolute value symbol is not needed in this problem. So our final answer is 30x to the 8th y squared times the square root of 2y. In this problem, we're going to find the product of two expressions. The first thing we're going to do is apply the square root of a product property, multiply them out, and there's our first step. And now we have 2 times 14 is 28, x squared times x is x cubed, and y times y is y squared. Well, we know that 28 is 4 times 7, and the square root is 4 is 2, so we'll bring the 2 outside of the radical symbol. And now we'll look at the x cubed y squared. Of course, x cubed is x times root x, and the square root of y squared is y. We don't need the absolute value symbol around the x, because if we're simplifying the square root of x cubed, we're assuming that x cubed is positive in the first place, and therefore x must be positive. But we can simplify the square root of y squared, whether y is positive or negative. So just in case y might be negative, we need to put the absolute value symbols around the y. So our final simplified answer is 2x times the absolute value of y times the square root of 7x. Here's the quotient of two expressions. We're not going to need absolute value symbols here because in the numerator we have an x. And since in order to take the square root of x and have it be a real number, x has to be positive. And in the denominator we have a y. And in order to take the square root of a y, y has to be positive in order for that square root to be a real number. So we won't have to worry about any absolute value symbols here. And then we're going to apply the square root of a quotient property. And now we can simplify 12/8 and get 3/2. And we can also simplify x over x to the 4th by getting an x cubed only in the denominator. And the y squared over y gives us a y in the numerator and no y's in the denominator. And now we're going to simplify the denominator. X cubed is the same as x root x, and the 2 stays in because there's not much we can do with root 2. And now we're going to rationalize the denominator by multiplying the entire fraction by root 2x over itself. Of course, that gives us root 6xy over x times 2x, because root 2x times root 2x is 2x. And now we need a little more room, and we write the root of 6xy, and we write x times 2x, recopied from the previous frame. And now, of course, x times 2x is 2x squared. And it looks like that's the best we can do. We know that 6 over 2 can be simplified, but the 6 is inside the radical. And since it can't be simplified anymore, we don't have any radicals in the denominator, we're going to stop there. The square root of 6xy divided by 2x squared is the best we can do. A reminder, the square root of a perfect square is equal to the absolute value of its base.